Alright, the learning objectives, because we already had gases once, so this will be gases part 2. Normally when we try to characterize a gas, we need to know its pressure, temperature, volume, and how much gas there is. Because if we have the volume, like 1 liter, it depends on how compressed that 1 liter of gas is. You could have more or less gas in 1 liter because gases are compressible and they're expandable as well. And so when we're buying gases, we usually buy gases by weight. How much does like an empty tank versus a full tank is going to weigh a different amount versus by volume. Anyway, there's a simple relationship between these, all of these. You know, we already talked about Charles and Boyle's, but we're going to talk about Avogadro's law and the ideal gas law today. Please with me. Physical characteristics of the gas. So it's just doing some algebra. 14.4, can you solve an algebraic equation that's the ideal gas law? 14.5, calculate the density. Well, there are a couple of applications of the ideal gas law. One is we can calculate the density rather than measure the density. Now, normally when we measure the density, it's a bit of a hassle because we've got to weigh it and then figure out its volume. But for gases, we can just go ahead and calculate the density of any gas, you know, if we know its molar mass. We'll talk about that. All right, given the density of a pure gas at a specified temperature, pressure, or information from which the density may be found, calculate the molar mass of the gas. So these two things are related, density and molar mass. So if we know the molar mass, we can figure out the density. If we know the density, we can figure out the molar mass. If it is a pure gas, or the average molar mass of a mixture. We have another thing that we use in stoichiometry. It's called the molar volume. The molar volume is, you know, under normal conditions. Under normal conditions, a mole of gas has 6.022 times 10 to the 23rd particles. 6.022 times 10 to the 23rd particles of nitrogen takes the exact same volume as 6.022 times 10 to the 23rd particles of oxygen. You know, and so it doesn't matter what the gas is. A mole of gas has a volume, and that volume is the same for all gases, and that's called the molar volume of a gas. The molar volume of a gas is super handy in stoichiometry. So molar volume we use stoichiometric calculations. I have this. It's so handy. I have this number memorized. You know, 1 mole of gas, any gas, at 1 atmosphere and 25 degrees C occupies a volume of 24.5 liters to 3 sig figs. You know, we didn't get it to more sig figs than 3, but 3 sig figs is about that. Okay, given the molar volume of gas, etc., calculate. We'll do some calculations with the molar volume. Molar volume, the easiest calculation is stoichiometry, but we can do other calculations as well. So if I had 1 liter, you know, how many moles of gas is that? Well, that's a fraction of a mole. So we can figure it out. Given a chemical equation or a reaction for which the equation can be written, the mass, this is stoichiometry using gases. You know, so far we've done stoichiometry with any compound, but when we do with gases, there are some shortcuts you can do. One of the shortcuts we can do is molar volume. And so we need to balance chemical equation to do stoichiometry. 14.9, 14.10, just stoichiometry. A lot of words are just stoichiometry. So this is Avogadro's law. It's also called the law of combining volumes. You know, the reason it's called the law of combining volumes is this. Here. So if we know the balanced chemical equation, let's say 1 mole of O2 reacts with 2 moles of hydrogen to give us 2 moles of, let's say, gaseous water. Normally water is a liquid. but in this case it's gaseous. Okay, so 1 mole of oxygen is 24.5 liters. 1 mole of oxygen. 2 moles of hydrogen, well, 24.5 times 2 would be 49 liters. And so if we take 24.5 liters of oxygen and 49 liters of hydrogen, that should be in the right ratio. That's 1 mole and 2 moles. Well, do I have to take the full 24.5 liters? No. What I could do is I could just take 1 liter. If I took 1 liter of oxygen, then how many liters of hydrogen do I need? I need twice as many liters because it occupies twice as much space. So this is a law of combining volumes. As long as the pressure and the temperature are the same, which it usually is in a chemical reaction, the pressure and temperature are the same, then we could take the mole ratio to be the same as the volume ratio. And so 1 liter of O2 for every 2 liters of H2. 1 gallon of O2 for every 2 gallons of hydrogen gas. It occupies twice as much. Now, here's the tricky part here. In this example, they're telling the product is gaseous, but normally we do this at 25 degrees C. If I did this at 100 degrees C, at 100 degrees C, gases expand in temperature, so that volume would be different. And so the situation with this is that in Chem 1A, this would be a liquid. And if this is a liquid, can we say that? So for example, if I have 1 liter plus 2 liters yields 2 liters. That's okay if they're all gases and they're at the same temperature and pressure. But if this is a liquid, then it's not the same, because 1 mole of oxygen gas at 25 degrees C in 1 atmosphere of pressure occupies 24.5 liters. 1 mole of liquid water, well, 1 mole of liquid water weighs 18 grams, so that's the molar mass. And so, how much volume does 18 grams of liquid water occupy? I mean, how much volume? Yeah, how much volume does 18 grams of liquid water occupy? 18 milliliters. And therefore, 2 moles of liquid water is 36 milliliters. And so, if that were liquid water, then I'd have 24.5 liters of oxygen, that's 1 mole. 2 moles of hydrogen, 49 liters. Forms 2 moles of liquid water. 2 moles of liquid water, 36 milliliters, 36 grams. And so you see, this law of combining volumes only works if everything's a gas and they're at the same temperature and pressure. And so liquid water, all the molecules would condense to the liquid state. And so this means stoichiometry is sometimes easier here, What this is showing is that if I have 3 particles, it occupies this volume. If I double it, the volume is going to double. So how many particles is this? 3, 6, 9. If I triple it, the volume triples. So the volume is directly proportional to the number of particles. In other words, volume is directly proportional to the moles of gas. That's Avogadro's law. So volume is directly proportional to the moles of gas. Here. We saw Charles' law and Boyle's law in the first one. And so if we combine all 3, we get a modified combined gas law. And so let me just show you this from earlier here. So from part 1, we saw this one, PV over T is equal to PV over T. Do you remember this equation? And so this is initial, initial, initial. This would be final, final, final here. We have this one too. We have P initial, V initial over N initial, T initial is equal to P final V final, N final, T final. So let's say you add some gas or you remove some gas. What impact will that have on the volume? What impact will that have on other things? And so we could use this equation to figure out if the number of moles of gas, N, this is where N is equal to the number of moles of gas. So if the number of moles of gas change over the course of reaction, then that's what we'll see. And so this is what this is trying to show here. V is proportional to T, is inversely proportional to E, which is proportional to N. So if we put all those variables on one side, this is what we end up with here. And that's equal to constant. There's one more equation that we can generate here. This is the ideal gas law. And so this is called the combined gas law. Combined or universal gas law. If the number of moles does not change, you don't add any gas, you don't remove any gas, then this simplifies into the earlier version that you saw. So these are the two equations that we deal with, the combined or universal gas law. And then we can rearrange this equation because this is equal to a constant. That's equal to a constant. And so if we rearrange that, we get the ideal gas law. The ideal gas law is that this PV is equal to a constant times RT. The constant, NT times NT, sorry. The constant we call R. And then I'll put it over here. So the constant is named R, which is called the gas constant. The gas constant has a number that we usually memorize. Let's see. Let's get the gas constant here. This is the gas constant here. This number we usually memorize at 0.08206. Units are very important. Let's say liters, atmosphere, mole, Kelvin. So 0.08206 liters times the atmosphere divided by moles times Kelvin. Memorize it. I don't know why they didn't give it earlier. Let me go back in PowerPoint here. For some reason, they didn't type it in here. I wish they would have just typed it here. But it's not here. So R is called the gas constant and it has a value. And so what we do is I'll just rearrange this to the form that everybody memorizes. You want to memorize that, and you want to memorize this. PV equals nRT. Pivner, some people call this the Pivner equation, or Pivner equation, something like that. This R is over here, and so this equation is not so hard to memorize. P equals nRT. Just those two equations. So all this stuff leading up to this is. So basically, there are only two things. One, we could do stoichiometry using volumes. We have gases. Stoichiometry is really easy. It's just by volumes. But the pressure and the temperature have to be the same for all gases. If the pressure and temperatures are different, then that's going to change the volume. And so let's say the oxygen was at one pressure and temperature and the hydrogen was at another temperature and pressure, then we can't do this. Because what we call the molar volume, which I'll talk about a little bit later, is different. And this is all leading up to this. What do we need to know? We need to know the ideal gas law. the ideal gas law is actually really all you need to know, because the ideal gas law, we can derive this equation, which is the combiner universal gas law. We could derive Boyle's law, we could derive Charles' law, we could derive Avogadro's law, because they're all incorporated into this one equation. And so basically, with the ideal gas law, you can forget about Boyle's, Charles, Avogadro's, solve all problems just using this and this. These are the only two equations you need to know. All right, so let's take a look at an example of a calculation. The 0.1000 mole sample of helium is placed in a piston and heated to 25 degrees C to 4 C-pigs. The volume is adjusted to 4.600 liters, and the resulting pressure is measured as 0.5319 atmospheres. Use these data to determine the value of the universal gas constant. Okay, they call this the universal gas constant. I just call it the gas constant. There's only one gas constant. There are different units that we can have for the gas. If you look in our book, they have a whole bunch of them. But the only difference is, rather than liters, we'll do it in milliliters. Rather than atmospheres, we'll do it in bars, so millimeters of mercury. So there are a whole bunch of different numbers, but you don't want to memorize all those. You just want to do simple conversions and get all the others. It's just one. All right, so basically, this P equals nRT. We aren't really changing. In order to characterize a gas, we need to know the pressure. Well, the pressure is given. It's 0.5319 atm. We need to know the volume. The volume is given. It's 4.600 liters. We need to know N. N is given, it's the number of moles, it's 0.1000 moles. And we need to know T, the temperature. The temperature, we cannot use degrees C. We always have to use absolute temperature. And we can't use the Celsius or Fahrenheit because of the zero issue. So it's going to be 298.15 Kelvin. And so what are we missing? Well, we're missing R. And so this is just some algebra. R equal to PV over NT. And then we plug in the units here. The pressure is 0.5319 atm. The volume is 4.600 liters. Divided by the number of moles, 0.1000 moles. Divided by the temperature in Kelvin, 290.15 Kelvin. So what does this come out to? So let's go ahead and do the calculation here. Okay, so I get 0.5319 times 4.6 divided by 0.1 divided by 298.15. What do you guys get? Well, I get that R is equal to 0.08206 liters atmosphere per mole Kelvin. I always do liters atmosphere. You can do atmospheres liter. It doesn't matter the order. So 0.08206. This is not an exact number. This is to 4 sig-pigs. So work down. Here, the pressure, the volume, the moles, the temperature, P equals nRT. Solve for R. That's it. Basically, this is what's going to happen. 4 out of the 5 are going to be given. And so all you have to do is calculate or solve for the unknown. It could be pressure unknown, volume unknown, moles unknown. Let's say you're going to buy some helium. You know the pressure of the tank, you know the volume of the tank, you know the temperature, you don't know the amount of helium in there. Well, you can get that and solve it for N. going to solve for one of the unknown variables, but we need 4. One of those 4 you have memorized, the ideal gas law, the universal gas law. I mean, we need 5. 4 out of 5. So. All right, the ideal gas equation, determination of a single variable. If all but one variable is unknown in the ideal gas equation, then use algebra to find it. So those are lots of calculations like that. This should be on a new slide, end of slide. Because that's determination of single variables is the first half of the slide. That's it. It says it's algebra. The second half of this slide is something different. So I don't know what Carcolici does this, but since these are the slides, I'll just give it to you as is. I won't change up because. Well, anyway, for this chapter, I'm going to follow along with the PowerPoint. Just follow along. Okay, so here we just did a representative calculation where we solve for R. This is not really represented because we've never solved for R. We'd never solve for R because you should have R. You should have R memorized, so we don't need to solve for R. What we're going to be solving instead for is P, V, N, or T. That's it. They don't go through more representative calculations. And so what we're going to do is we're going to look at other applications. So, application 1, which is the first half, solve for missing variable. Solve for the missing variable. Application 2, determine the molar mass of the gas. Wait, no, this is not determining the molar mass of the gas. I see what they're doing here, but I wouldn't do it like that. These are specialized applications. And so option 1, option 2, determine A, the molar mass of the gas. This is the way I would have done it here. Molar mass of the gas is equal to the grams of gas per mole of gas. So we need to know how many grams of gas are in a mole. Like, for example, the molar mass of helium, what is it? It's 4 grams per mole. Or 4.00, what is it? 4.0 something. And so we need to know how many grams there are per mole of gas. Well, we could get that, if we knew it, we could just figure it out based on the periodic table. What's the molar mass of CO2 gas? For example, CO2 gas, carbon weighs 12.01, 2 oxygens is, well, each oxygen is how much? 16, so 2 of them are 32. And so for CO2, the molar mass of this gas is 44.01 grams per mole. And so why do I need to know this equation for the molar mass of a gas? Because the molar mass of the gas is easy to calculate if I have the periodic table, right? So it seems ridiculous to have this equation to do it. And so we need to add something here to this. This has got to be the molar mass of an unknown gas. Now, of course, if I don't know the formula, then I can't calculate its molar mass, right? And so this has got to be unknown. Otherwise, there's no use in doing this equation because it's kind of a waste of time. If we knew what the gas is, then why bother doing an experiment to measure its volume, temperature, all this other stuff? It just seems kind of ridiculous. And so this time I said I was gonna follow the slide, but I'm gonna veer off from the slide a little bit. And let's talk about how to determine the molar mass of an unknown gas. Unknown gas. Okay, so what I need is I need the mass of gas. I'm just gonna rewrite that in a different form, divided by the moles of gas, except in this case, mass of gas, I'll just call it mass, like this. I'm not gonna use their symbol for mass. Their symbol for mass is M, but we usually use this for meters. And so I'm just going to write it out as mass instead of using M, so there's less confusion. But N is the standard symbol for moles of gas. And so I'm going to use N, the gas. And then what we're going to do is we're going to use the ideal gas law. If we solve the ideal gas law for N, we get N is equal to PV over RT. So I'm just rearranging the ideal gas law. And then I'm going to substitute this in here. If I substitute that in there, I get the mass of gas divided by PV over RT. And so we could solve this here. What I'm going to do is I'm going to flip this over. And so this is going to equal the mass of gas, right, times RT divided by PV. Okay, so what do I need to do to figure out the molar mass? Tell me what I need to measure. In order to calculate the molar mass of an unknown gas, what I need to measure is how much it weighs, the temperature, the pressure, and the volume. It's a lot of work. That's a lot of work. But if it's unknown gas, it's worth it. But there's something else that we can do and that something else is sometimes it's easier to get the density. And so, you know what mass over volume is? Density. And so sometimes we know what the density is. We can look it up in a table. And so what we end up with is this. The molar mass of the gas is going to equal the density of the gas times RT over PV. Actually, we don't need V anymore because V is incorporated into the density. So if we're given the density and the pressure and the temperature, we can determine the molar mass. And so need the density, the pressure, and the temperature to get the molar mass. That's one application. Another application is this. And so this would be B. We can determine the density. The density of a gas is equal to this. It's equal to this has to be a known gas. We need to know what the gas is in order to use this equation that I'm going to give you. And so the density of a gas, and this is a known gas, is equal to the mass of the gas divided by its volume. And so we have to measure two things. We have to measure the mass and the volume. Okay, for an unknown, we'd stop there. But for a known gas, we do this. We know that the volume is equal to nRT over P using the ideal gas law. This only works for gases, by the way. Density of a known gas. And so what we're going to end up with is that we're going to have the mass of the gas divided by the volume. Well, the volume is nRT over P. And so we'll invert and multiply. If we invert and multiply, we're going to get the mass of the gas times P divided by nRT. Now, what is mass over mole? Like grams per mole. Grams per mole, have you heard that unit before? That should be recognizable. If we know the grams per mole, that's what we call the molar mass. And so this is the molar mass, which we'll abbreviate MM. And so this is it. We have the density of the gas is equal to the molar mass of the gas times P divided by RT. So what this equation allows us to do is this equation allows us to calculate the density of any gas at any pressure and temperature, as long as we know what it is. Allows the calculation of density at any T and P. So let's say I'm kind of curious, what is the density of helium at 100 Kelvin and 100 Kelvin and 0.5 atmospheres? Do I have to do a measurement? Do I have to take measurements? No, I'll just plug it into this equation. So density of a known gas, well, I need to know the gas because I got to figure out the molar mass. So CO2, we just figured out the molar mass is 4401. So now, if I know the molar mass of the gas, I can calculate its density at any temperature and pressure. Now, do I need this equation to determine the molar mass of CO2? No, I just use a periodic table. So this one's only for an unknown gas. All right, since I already veered off the PowerPoints, there's one more calculation that we do that is common. And that's something called the molar volume. So I'm just going to add it to this list. We call it ABC, molar volume. To the volume of the gas per mole. So if I have a mole of gas, what's its volume? Well, that's a molar volume. You know? Or let's say I had 100 liters of gas. How many moles is it? So molar volume. Well, the molar volume of the gas, I don't want to measure it. I just want to calculate it. So there are different things we could do. So for example, one of these, let's see, we can make this a little easier. Let's substitute either for moles or for volume, one or the other. And it doesn't really matter which one we substitute for, I think. Let's substitute for moles. We know that the moles of gas is equal to, solving the ideal gas laws, equal to PV over RT. And so we'll substitute that in here. And so we get the volume of gas over PV over RT. And then what we're going to do is we're just going to invert and multiply. When we invert and multiply, we just get volume times RT over PV. Well, V cancels. So we end up with is RT over P. So we can calculate, 1 mole of gas at any temperature and pressure. Well, what's the most common temperature and pressure? So the molar volume of the gas is equal to RT over P. This is a really useful number to know. And so what's a common pressure and temperature? The common temperature is 25 degrees C, which we call room temperature, or 298 Kelvin. Let's just say 298.15 Kelvin. Room temperature. RT stands for room temperature. And pressure of 1 atmosphere is fairly common, so we'll just go exactly 1 atmosphere and 25 degrees C or 298.15 Kelvin. And so what is the molar volume? The molar volume of this gas at this temperature and this pressure is equal to RT over P. R is 0.08206 liters times atmosphere divided by mole times Kelvin. T is 298.15 Kelvin. P is, we're just going to do 1 atmosphere, exactly 1 atmosphere. So infinite sig figs here. So atmospheres cancel, Kelvin cancels, and that leaves us liters per mole. So let's figure out how many liters per mole that is. I have the number memorized, 24 and a half, but that's to 3 sig figs. What if I wanted it to 4 sig figs? Well, let's see what it is. And so I'm going to go ahead and punch this out. 0.08206. 0.08206 times 298.15. It's 24.466. And so the molar volume, probably this is what you need to know. 24.466 liters per mole. And so we're going to round this to 4 sig figs, 24.45 liters per mole. Molar volume at 298.15 K in 1 atmosphere. So 24.45, or about 24 and a half liters in a mole of gas. Those are what we call useful variations of the ideal gas law. And so that should be a separate slide in itself. So let's look at some calculations. Let's see. Got here. Ideal gas law. Then we're going to do some more applications. What is the pressure in a helium-filled 0.77 liter balloon if it contains 1.0 grams of gas at 22 degrees C? So what do we need for the ideal gas law? We need pressure, volume, number of moles, R, and temperature. So what do we have? We have the pressure. No, the pressure is what we're solving for. So if we're solving for pressure, we need nRT over V. And so they give us V. V is 0.77 liters. They give us T, which is 22 degrees C, or plus 273 would be 295 Kelvin. We know what R is. R is memorized, 0.08206 liters times atmosphere per mole Kelvin. We need N. Do they give us N? They don't give us N, the number of moles. But we can figure it out because this is just a gram to mole conversion. Gram to mole conversion, we just need the molar mass. The molar mass of helium is 4.003. We'll do 4.003. So we're just going to do grams per mole. Actually, we only got 2 sig figs here. 1.0 grams of helium. And a mole of helium weighs 4.0. Yeah, we'll just go with that. 4.0. You know, the convention is if I'm given 2 sig figs here, I better use at least 3 here. But I don't want to change this because I have this memorized. And so, you know what? It's 1/4 mole. So 0.250 mole. We got it. Now we got all the numbers. We just plug it in. This is solving for a single variable. To me, I don't want all kinds of variations of the ideal gas law. I wouldn't have done it like this. I would have just said, okay, I'm giving grams, I could convert it to moles. I'm not going to modify the ideal gas law to fit what I have. That's one of the failings, I think, of this book. The approach, but it's fine. It's not really. It's a lot of equations. So, for example, if you're doing this in milliliters, what they'll do is they'll give you a new R. Well, that's another R you have to remember. Why not just convert milliliters to liters first, and then just plug it into your usual equation? Does that make sense? The same thing. If I'm given grams, why not just go convert grams into moles and then use the same equation, right? And so my thinking on this is just get all the variables into the proper units and then use the same old equation for every single calculation. The only time you can't do that is when we're doing molar mass, molar volume, and density. Molar mass of an unknown, that is. I don't think we're going to do the molar mass of an unknown. And so they like to do this. The same thing with R. This is why they give like 10 different R's there, because they want to, they don't want you to have to convert units. And so for me, I would just plug this in. I know what the T is, plug that in. I know what R is, plug that in. I know what N is, and I know what V is. Just plug those in. Same old equation. No new variation. And so let's see what I've gotten the same. So I'm just plugging N, 0.25. Yeah. One advantage, though, of plugging it all in one equation is no round off, because I rounded this off. I dropped the 0. I'm going to get the exact same answer. So 0.25 is N times 0.08206. We got to make sure the units work out. We always want to make sure the units work out, so it's worth doing. You see how they crossed out the units there? So I'm going to plug in 0.250 moles times R, which is 0.08206 liters, atmosphere per mole Kelvin, times temperature 295 Kelvin, divided by the volume 0.77 liters. So just to make sure the units work out, or the dimensions, well, the moles cancel, the Kelvin cancel, the liters cancel, that leaves us with atmosphere. And so 0.25 times 0.08206 times 295 divided by 0.77. 7.85. Atmosphere, which they rounded to 7.9. Correct number C. So you got this. It's just memorizing a whole bunch of equations is too much. So we did the density. They derived density a different way than I derived it. So the equation PV, that can be solved for density. The way I solve for molar mass, the way I solve for density is the same. I just use the definition of molar mass, grams per mole. I use the definition of density, grams per liter, or grams per, mass over volume. Mass over volume is the definition of density. So the way I did density is I started with this M over V. I did a substitution for V, and I came up with this equation. This is different than the way your book is doing it. But I don't want to memorize this equation. In fact, I want to do the minimum amount of memorization possible. What is the density of helium at 22 degrees C? Now, you have two choices here. You could memorize the density equation, or you could derive it. The derivation for the density equation is fairly straightforward. And so the density of a gas, actually, if you forget it, it's just the mass over the volume, and then just do a substitution. You remember that the volume is equal to nRT over P, just rearranging the ideal gas law. And then just plug that in. It's going to be the mass over nRT over P, which gives me the mass times pressure over nRT. Well, here you have to see something. Mass over moles, grams per mole. Grams per mole is what we call the molar mass. So this is the molar mass times P over RT. So if we want the density of helium, we need to know the molar mass of helium. The molar mass of helium, we look off the periodic table, it's I'm going to go one more digit, 4.002. 4.003. Since we're going to suffer a little bit of round off here and there. Grams per mole. And so we'll just plug it in here. Unfortunately, know how to derive. Because unfortunately you're not always given this equation. So you'll have to be able to derive it yourself. So we plug in the molar mass, 4.003 grams per mole for helium. Plug in the pressure. The pressure is 744 torr. Your book gives a different R for when we use torr, but you know the easiest is this. Now I'm going to do a variation here. I know I need the pressure, but I need the pressure in atmospheres. And so what I'm going to do is I'm just going to go ahead and give myself 744 torr here, and then just convert it into atmospheres by multiplying it. 1 atmosphere is equivalent to 760 torr. The torr is the same as a millimeter of mercury. So we could look that up in the book, or you have it memorized. Then we use R. Well, torr cancels out torr. That leaves us with atmosphere. So I didn't separate it this time. I just incorporated it here. Divided by R, 0.08206 liters times atmosphere per mole Kelvin times T. Temperature is 22, so 22 plus 273 is 295 Kelvin. So Kelvin cancels, moles cancel, atmospheres cancel, and that gives us grams per liter. So what is the density of helium in grams per liter? Just go ahead and go through the calculations here. It's going to be 4.003 times 744 divided by 760 divided by 0.08206 divided by 295. 0.1618. How many sig figs are we allowed? It's like 3 sig figs. 0.1618 grams per liter. It's very low density. Well, you expect helium to be very low, but so here they have the equation. Density is equal to the molar mass times pressure over RT. That's what we have here. Molar mass times pressure over RT. What's different about our equation and their equation?
The way they converted the torr, right?
They didn't convert torr.
Well, where they got the 62.4 liters like that.
Yeah. Where did this 62.4 liters come from? this is where I have a different philosophy than your book's author, Krakalici. Let me tell you where the 62.4 liters came from. Liters or personally, I just want to memorize one R constant. Your book, though, wants you to memorize many R constants because R, I remember, is 0.08206 liters times atmosphere per mole times Kelvin. Well, what if I'm not using atmospheres? What if I'm using torr? If I'm using torr, well, it's easy. We just switch this. We know that there's 760 torr for every atmosphere. And so what we can do is we can get rid of the atmospheres and get torr instead. Well, what does this come out to? Well, what is 760 times 0.0826? So go ahead and do that. 0.08206 times 760. This equals 62.365. This is exact, so I'm allowed 4 days. And so your book asks you to remember this. This is liters times torr per mole times Kelvin. And so in the book it lists it's equal to 62.4 liters torr per mole Kelvin. And so where did the 62.4 come from? The 62.4 came from the book. And that's why they have so many, because, so for example, what if we didn't use liters? What if we used gallons? Then we have a different number here. Because it's 3.78 liters in a gallon, so it's going to change the number. And so you got so many different numbers here that you can come up with. But what's easier for me is to convert, rather than convert R into a new R, what's easier for me is just to convert torr into atmospheres, because we should know there's 764. So my feeling is just ignore all these other units for R. I wouldn't even bother memorizing them. And so I got 0.1618, which rounds to 0.162. This is another thing I don't like, is they don't show the rounding step, which I'd like you guys to do. 0.1618, which rounds to 0.162. So they derived the molar volume like I derived all the others. The definition of molar volume. The definition of molar volume is the volume per mole. How many liters per mole? And so we, except they did it differently. They solved for V and substituted it in. I solved for N and substituted it in, but it doesn't matter. Whether you solve for V or you solve for N, you'll get the exact same answer when you substitute it in. And that is the molar volume is equal to RT over P. And so what we can do is we can show we can calculate the molar volume at any temperature and pressure, which we did. 24.45 liters per mole at 1 atmosphere, 25 degrees C. Is 25 degrees C the standard temperature? What do you call 25 degrees C? Room temperature. It's a little warm for room temperature, but that's this agreed upon room temperature. There's another temperature that you got to remember, and that's called standard temperature. Standard temperature is only for gases. Standard temperature is not room temperature. Standard temperature is 0 degrees C. 0 degrees C. So standard temperature, so if somebody says room temperature, 25 degrees C. If somebody says standard temperature, 0 degrees C. Those are the two temperatures you got to know. And so, 0 degrees C is pretty cold. So if you take a gas from room temperature and you freeze it to 0 degrees C, gas doesn't freeze, it just gets cold. And so if you take that gas and you cool it down to 0 degrees C, what's going to happen to the volume? It shrinks. Well, how much did it shrink by? Well, we can calculate the molar volume of the gas at 0 degrees C, and actually, it's not room temp. I mean, pressure is a little bit different. This is 1 bar. Is 1 bar the same as 1 atmosphere? No, it's not. Fortunately. Is it close? It's very close. You know what's bigger, a bar or an atmosphere? Well, do you know the relationship? Bar. You don't have to have that memorized. But that came back from, what chapter was that earlier that we were looking at? Gases. Gases part 1 was chapter, boy, my memory is bad. Chapter 4? It's a roundabout way of getting the bar. So, 1 atmosphere is equal to 101,325 Pascal. 1 bar is equal to 100,000 pascals. So, putting those two together, we get that 1 atmosphere is equal to 1.01325 bar. Putting those two. But you don't have to memorize this. This would be given. So I don't expect anybody to memorize this unless you've had physics. You had a lot of physics, then this number would, you'd probably remember if you've done a lot of calculations. So that's where that conversion came from. And so this is what we're going to do. Do you know there's an R? There's an R? I don't want to memorize too many R's. You know, I just want to memorize 1 R. And if I'm not using atmospheres, I just make sure I convert it to atmospheres before I plug it in here. Crocolici, he wants you to memorize lots of different R's, so if we're using bar instead of atmospheres, he's going to have a different number here. Right? Too many numbers is too confusing for me because my memory's not so good. And I'd rather just memorize 1 than convert, because this conversion factor is going to be given. I don't have to memorize this one. And so this is the way I do. Let's figure out the molar volume of a gas. This time, this is just going to be an example. We're going to do this at 298.15 Kelvin, which we call RT, and 1 bar. Now, I ask you, which one's bigger, a bar or an atmosphere? Take a look at this conversion factor here and tell me which one's bigger, a bar or an atmosphere? Which one's bigger, a bar or an atmosphere? I hear 2 responses there. So you'd say atmospheres, Nick? How many people say atmospheres is bigger than a bar? 1 atmosphere is bigger than 1 bar. Okay, 1 person. How many people say a bar is bigger than an atmosphere? Well, when you look at this, you know what it turns out? It turns out an atmosphere is bigger. An atmosphere is bigger because you can fit more than one bar inside an atmosphere. Whereas if we look at it from the bar's perspective, one bar, okay, if I wanted to figure out, it's going to be equal to 1 divided by, they're very close, 1.325 atmospheres. We could use dimensional analysis for this, but I'm skipping the dimensional analysis. Just go straight. And so, let's see, figure out what it is. 1 divided by 1.01325. Oh, come on. Here, calculator. 1.225. It turns out one bar is almost one atmosphere, not quite. The atmosphere is a little bit bigger. We get 0.9869 atmospheres from one bar. It doesn't matter. They're very close. And so a lot of people say a bar and an atmosphere are about the same. So if we use them interchangeably, then it's not going to be a huge error. We can expect about a 1% error in the calculations if we don't bother converting one to the other. But anyway, let's go ahead and redo this calculation for the molar volume of the gas. So the molar volume of the gas is equal to I remember that. I have it memorized, RT over P. But can you derive it? If you forget this equation, you can derive it. Right here. If you forget the equation, you got to remember that the molar volume is equal to volume over moles. If you forget it's equal to RT over P, then it's not hard to derive because we use the same technique. And so, if I forgot this equation, I would have said the molar volume of the gas I know is the volume per mole. How many liters per mole? Like that. This you have to have memorized. Just like density. Density is mass over volume. Density is mass over volume. Molar volume is volume over moles. And then substitute. They're substituting V. I substituted N. It doesn't matter because we get the same thing. You either substitute V or N. But I did N is equal to, you know the reason why I did N rather than V? Because all three equations I solved in the same way on the denominator. If you look back at the density, I substituted the denominator. If you look back at the molar mass, I substituted the denominator. If you look back at the molar volume, I substituted the denominator. So I'm just being consistent. And so N is equal to PV over RT. Plug that in. So we get V over PV over RT. Well, V's cancel. Flip, invert, and multiply RT over P. Okay, R. I don't want to memorize a whole bunch of R's, so I just have one. 0.8206 liters times atmosphere per mole Kelvin. Now your book has a different R value for bar. But what I'm going to do is I'm just going to convert from atmospheres to bar. And so I have one bar. Let's go with exactly one bar. Exactly one bar, so I don't have to worry about sig phase. And so I know the conversion, well, or I'm given. This one I don't expect you to have to memorize, but 1 atmosphere is equivalent to 1.01325 bar per atmosphere. Did I do this right? No, I need to cancel out. Sorry, I didn't do this right. So I have R times T. T is what? 298.15 divided by P. P is 1 bar. I don't know, for some reason I put it in the numerator. P goes into the denominator. This is 1 bar. Now I'm going to convert it. 1 atmosphere is equivalent to 1.01325 bar. I'm using this many sig figs because I just have it memorized like that and I don't want to round it. So bar, bar, atmosphere is atmosphere, Kelvin. That gives me liters per mole. So bar is a little bit less pressure, so I said 24.45, but if there's less pressure, the gas grows. If there's more pressure, the gas contracts. It depends on how much pressure. And so now there's going to be a little less pressure because the bar is a little smaller. And so it's going to come out to 0.08206 times 298.15 divided by, or times, in this case, 1.01325. So a little bit less pressure, it's going to expand. It expands to 24.790 liters per mole. So under a pressure of 1 atmosphere, it's 24.45 liters. Under a pressure of 1 bar is a little less. It grows a little bit. Not much, but it grew a little bit, 4.79. Okay, what happens when I cool it down? If I lessen the pressure, it grows a little bit. If I cool it down, it's going to contract. So let's go ahead and do this. Oh, actually, they did the conversion here. They did it like I would do it. In the old book, they didn't. In the old book, they gave a whole bunch of different R's. But the other thing is, when I round things, numbers that I memorize, numbers that I memorize, I don't round. I just use as is. I don't know why they're that. I mean, if you got to memorize the 4 sig figs, why not just use all 4 sig figs? I'd understand if you only memorized it to 3 sig figs, but if you're memorizing it to 4 sig figs, it just makes no sense. And so the next example is the molar volume at 0 degrees C, which is 273 Kelvin, and 1 bar. So we're cooling it down, it should shrink. So the molar volume is equal to RT over P. So R is 0.08206 liters atmosphere per mole Kelvin. So why go through the extra step of rounding that? It doesn't make sense. Times 273 Kelvin divided by the pressure. The pressure, we're going to do exactly 1 bar. So there's no sig fig issue here. It's infinite sig fig. And then convert it. Well, I've had to memorize this. I've never forgotten it. And so it's 1.01325 bar and an atmosphere. Well, maybe I forgot. If you get reminded, then remember. Since I haven't memorized to that many sig figs, I don't bother rounding it because rounding it's an extra step. Extra steps take time. And so the gas constant, don't bother rounding. This one I don't round unless I'm looking it up in a book, then I round it. Atmospheres cancel, Kelvin cancel, that gives us liters per mole. So let's see what it comes out to. So I'm going to use my numbers, 0.08206 times 273 divided by, or times in this case, I need to back up here, times 1.01325. 22.69. The 3 sig figs to allow 22.7 liters. Well, they got the same answer. What is the molar volume of air at 11 degrees C? 1.33 atmosphere. many liters per mole would I have? Okay, molar volume of air at 11 degrees C and 1.33 atmosphere. Hey, air, is that pure or mixture? It's a mixture. Well, it doesn't matter. Let's see. Molar volume of air is equal to PV over R. Or no, sorry. It's wrong. Molar volume of air is equal to RT over E. Hey, does it matter if it's air? No. The only thing it matters is density. You know, because 22.7 liters of helium versus 22.7 liters of oxygen, they're both 1 mole under these conditions. But they're going to weigh different amounts because a particle of helium only weighs 4 U, whereas an O2 molecule weighs 32 U, so O2 is going to be a lot more dense. And in this case, it doesn't matter. We don't even need to know that. This is RT over P. So, actually, this one, we'll just look at the slide here. One, the temperature cannot be left in C. We have to convert it to Kelvin. This is the first step. They convert it to Kelvin. Pressure in atmospheres is fine. In fact, that's what we want. Molar volume equation here. Volume over N. And the other way of solving this is just put these two variables and solve the ideal gas law. That's what we come up with. P times B is equal to N RT. So take the B divided by N, divide both sides by N, divide both sides by P. What do you get? RT over P. Okay, for their R here, they did it again. We're going to memorize this to 4 sig figs. I'm thinking they're saying to memorize it to 3 sig figs, but in Chem 1A, you need to memorize it to 4 sig figs. And so rather than memorize it to this and then have to re-memorize it to 4, just start off with 4. 0.08206. We get a molar volume of 17.5 liters per mole. It's a pretty small molar volume. It shrunk down a lot. It shrunk down a lot because both things are going to shrink down the volume. Cooling the gas down shrinks its volume, and increasing the pressure shrinks its volume. So both of these will shrink the volume of the gas. Okay, next what we're going to do is we're going to take a look at gas stoichiometry. STP. Do you know what STP stands for? Standard temperature and pressure. This is the molar volume of gas at STP. Standard temperature and pressure. This is the pressure of 1 bar. It's 22.7. A lot of people will, a lot of instructors will make you memorize this. 22.7. But not me. The reason I'm not going to make you memorize that is this. How many labs are set up to do reactions at 0 degrees C? How many laboratories are there out there at 0 degrees C? None. Yeah. Maybe one. I don't know. I've never heard of it. So, does it make sense to do stoichiometry at 0 degrees C if your lab is not set up to do work at 0 degrees C? versus how many labs are set up to work at room temperature? All of them, most of them. And so, you know what? I don't even bother. I remember when I was a Chem 4 student, I memorized the molar volume of the gas at STP. I've never forgotten it. Do you know in all these years how many times I've used the molar volume of the gas at STP? 0. I memorized it and never used it again. What a waste of precious memory. So, you know, that's because our lab was not set up to work at STP. Gas stoichiometry at STP, our lab certainly wasn't set up. Maybe some lab out there is set up to work at standard temperature, which is 0 degrees C. But I've never heard of it. And so, do you know what I'm going to do? I'm going to skip this. That's okay. Let's skip this. Did I skip too far? All these techniques are good, except we're just going to apply it not at STP, we're going to apply it at other temperatures. Does that mean you're, I cycled through all those slides and then, what if I'm not at STP? And so this is the point of this. When I look at this is not specific for STP. And so what we have here is this need not be at STP. This should just be labeled gas stoichiometry, this one. We could be at STP or we might not be at STP. It doesn't matter. We should be able to do gas stoichiometry at any temperature and any pressure. And most of this stoichiometry map you've seen before. The only new thing is this. Let me just show you here. Let's just focus on the new rather than all the old stuff there. If you go back to the old gas stoichiometry maps and compare this one with the previous ones, you'll see one new thing. So, the one new thing is this. To get to the heart of the stoichiometry map, which is the mole-to-mole conversions, we go from moles of A to moles of B using the balanced equation, mole ratios. So the only difference is this. We're starting off with the volume of gas A. So if we know how many liters of gas, like 10 liters of oxygen, we need to figure out how many moles that is. There are two ways you could do that. One, we can use this one. N is equal to PB over RT. We'll just solve the ideal gas law for the unknown. The unknown is N. And so we do an algebraic equation. solve for N. Once we get N, that's moles of A. Or 2, we use dimensional analysis. Dimensional analysis, we figure out the molar volume. The molar volume is moles, this volume over moles, we'll flip it over. And so if we use dimensional analysis using molar volume, upside down molar volume, 1 over molar volume. So let's just do an example of that first part there. I have 10 liters of O2. How many moles of O2 is that? Well, I have 2 ways to figure it out. One way of figuring that out is this moles of O2 is equal to PV over RT. So what do I need to figure out? I need the pressure. So let's go with the pressure. Let's use, pressure should we use? Let me see what pressure is common here. So what we're going to do is we're going to say the pressure is 1 bar. Let's say exactly 1 bar. What temperature should we use? Temperature, we just use 298 Kelvin, room temperature. This is going to go with 3 sig figs. Alright, so we'll just plug it in here. Pressure is 1 bar. Volume is 10 liters. We'll just say exact. R is 0.08206 liters times atmosphere per mole times Kelvin. The temperature is 298 Kelvin. The units work out except for this. Liters cancel. Atmospheres doesn't cancel bar. So we need to convert. Yes, and so we'll just say 1 atmosphere is equivalent to 1.01325 bar. So the bars cancel, the atmospheres cancel. We've got good for moles. We have 1 over moles. We convert and multiply. That gives it to us. And so this is going to be 10 divided by 0.0826 divided by 298 divided by 1.01325 1403. This is called the algebraic way of doing it using the ideal gas law. Next, we're going to use the dimensional analysis way. Okay, for dimensional analysis, first we have to solve for the molar volume algebraically. The molar volume is equal to RT over P. And so R, okay, this is molar volume at 298 Kelvin and 1 bar. We We already did this. Do you remember what the molar volume is? Yeah, I mean, the number. We did this calculation a little bit earlier today. Can someone write down the number? The molar volume at 290 Kelvin 1 bar. It's okay, it's a simple calculation. We can just do it again. 0.08206 liters times atmosphere per mole times Kelvin times the temperature, 290 Kelvin. I did 298.15 Kelvin divided by the pressure.
Is it just the number?
Okay.
24.7.
24.790 liters per mole. Okay. Can you memorize this? This is a useful one to memorize.
Sure.
You don't have to memorize it. The reason I'm saying this is because most instructors will ask you to memorize this. Most instructors, including my Chem 4 instructor, ask me to memorize this number. I memorized this number. I still haven't memorized. I memorized it when we were using atmospheres. It's 22.4. 22.4. When we switch to bars, it's 22.7. But still, this number is not very useful because of standard temperature. This number will save you time. If you have this number memorized, look at what happens here. If you have 10 liters of oxygen, we go 10 liters, and then you have this one memorized. For every mole, we have 24.79 liters. I don't quite have it memorized. Do you see that? And then I have the answer here. Why is that useful? Why that's useful? Because most chemical reactions are done under conditions of 1 bar, which is, atmospheric pressure, black pressure varies day to day. And room temperature. So I can figure it out. So let's fill out the map a little bit more. Volume of a gas. We could go to moles of a gas by using 1 or 2. And then we just do a mole to mole conversion, so we can get mole to B. If B is a gas as well, then we can go to volume of B gas. Volume of B gas, which is a product or another reactant, is done by using 1 or 2. This is a standard. Sorry. The central part is standard. The advanced part is this. Advanced part is if we have a mixture, like air. Is air 100% oxygen? No, air is only about 80% oxygen. And so what if we're given the volume of a mixture like air? If we're given the volume of the mixture, then we have to figure out, out of that, like 10 liters, if I had 10 liters of air, do I have 10 liters of oxygen? No, I don't. I have a lot less. And so an example would be something like this. 10.0 liters of air equals how many liters of oxygen? So this is an extra step here. So if I have 10.0 liters of air, I need to know the percentage. Well, it turns out the mole percentage for gases percentage is equal to the volume percentage, which is equal to the pressure percentage, which is not equal to the mass percentage. And so for air is approximately 80% nitrogen, 20% oxygen. Is that by mass or is that by mole? By mole. By mole. And so what that means is for every 20 moles of O2, I'm going to have 100 moles of air. Well, it turns out that the mole percentage is the same as the volume percentage. And so what that means is that for every 20 liters of O2, I have to have 100 liters of air. And so if I have 10 liters of air, then there are only 20 liters of O2 for every 100 liters of air. Because air is 20% by mole, or 20% by volume, O2. Does that make sense? And then we can go from liters of air to liters of O2. Once we get liters of O2, then we use method 1 or 2 to get this to moles of O2. And so what I'm going to do is I'm going to redo their problem, but not at STP. What volume of hydrogen measured at STP can be released by 42.7 grams of zinc as it reacts with hydrochloric acid? STP is unrealistic. And so let's do this under normal laboratory conditions. What are normal laboratory conditions? Laboratory conditions are going to have pressure. Normal laboratory conditions used to be 1 atmosphere, but now we're using 1 bar. An atmosphere and a bar are very close, not a huge difference. The answer is going to be close whether you use bar or atmosphere. But let's see. We'll redo this problem with the temperature equal to what? We're going to redo this problem with the temperature equal to room temperature, which is 298.15 Kelvin. And the pressure equal to 1 bar, standard pressure of the, I guess, non-standard. Zinc reacts with hydrochloric acid. They gave us the equation, but I expect you to be able to figure out the equation here. Zinc reacts with hydrochloric acid. It's a redox reaction. This one double replacement works. I mean single replacement works because this is a mineral acid. So we're going to end up forming zinc chloride plus hydrogen gas. To balance it will be 2 HCl. That's what they have here. And so 42.7 grams of zinc. So what we must have is excess hydrochloric acid. This is excess hydrochloric, so it means we have So the limiting reagent here is going to be the zinc, or LR. So 42.7 grams of zinc. We do this via dimensional analysis. So I'm just going to start off 42.7 grams of zinc. And then what we're going to do is just, if I want to map this out, I'm going from grams of zinc to moles of zinc. From moles of zinc, I'll go to moles of hydrogen. From moles of hydrogen, I'll go to volume of hydrogen gas. So that's kind of on the tail end stoichiometry map here. So we're going to use it using the molar volume method. Molar volume method first. So I'll go 42.7 grams of zinc. So I need to cancel out grams of zinc. I can use the molar mass to do that. Because it's zinc is 65.39. So mole of zinc weighs 65.39 grams. So grams of zinc cancels, that leaves us with moles of zinc. Well, I can go from moles of zinc to moles of H2. It's a 1-to-1 mole ratio here. And so 1 mole of H2 is formed when 1 mole of zinc reacts. So moles of zinc cancels. That leaves me with moles of H2. Now, do you have the molar volume memorized? Well, it's a useful one to memorize because it'll save you a lot of time. If you do, it's 24.79. Did I memorize that correctly? Was it 24.79?
Yep.
24.79 liters for every mole. This one is only valid though at what temperature and what pressure? Room temperature and standard pressure. And so this one's only valid at RT and 1 bar. If I change it, it's going to change the number. But why bother memorizing this one? Because most of our reactions are at RT and 1 bar. And so this saves you a little bit. And so from memory. Or calculation. If you ever forget it, the molar volume is equal to RT over P, and we can calculate it. All right, so let's see how many liters of hydrogen we get. It's 42.7 divided by 65.39 times 24.79. 16.18. Which rounds to 16.2 liters. All right, what happens if I cool that 16.2 liters down from room temperature is 0 degrees C? It's going to shrink. So what they did was they did the calculation at 0 degrees C. So let's see what they got for the volume. You see, what did they memorize? They memorized a different number. They memorized 22.7. Is that a useful one to memorize? No. The only time you're going to use it is for these calculations. So I don't even bother memorizing this one. And so do you see, we got 16.2 liters, they got 14.8 liters because as you cool the gas down, it's going to shrink. Shrinks. What time are we out today? 25?
25.
Okay, I guess we're out of time then. Is that 25 early or normal time? Is it 25 or 35?
25.
25, okay, we're out of time. All right, I'm going to stop here.